In this math counts preparation lesson, we're going to be exploring some more probability. We're going to be doing 2 probability problems, which are a little bit different than the ones we've been doing in the past. I have a video on for math counts preparation on combinatorics and probability, which a lot of probability is just combinatorics. It's just modified combinatorics, but today we're going to look at some different probability problems. We're going to do a little bit of a refresher here. If you haven't watched the combinatorics and probability video, then I suggest you go ahead, watch that. You'll get all the probability information you need. But basically, we're going to start off with the probability is just it's basically just the total, like, possible outcomes. And it's like, and over that you're going to have the desired outcomes, or the ones that you want, so it's desired outcomes. So that's the probability of an event. So basically I'm going to give you an example, like if I have a fair coin, what's the probability that I get heads? If I flip a fair coin once, what's the probability that I get heads? So the probability that I get heads So what is the probability that I get? Go ahead and try this one. This is a very easy example. So as what we're going to do is we flip it once, we can either get heads or tails. So there's 2 possible outcomes. And we want heads, and there's only 1 heads. There's heads and tails, so the one we want is heads, so it's 1/2. That's basically a very easy example of probability. Now you have to have some experience with probability problems, like geometric probability. I suggest you go watch all the probability things because we're going to be doing probability problems which require some of those skills. Desired, possible, probability to get heads. Let's go to dice. What's the probability that you get a 6? So the probability that you get a 6. If you roll a fair 6-sided dice, what's the probability to get a 6? Now, for those of you who are experienced in probability, which I hope most people are here who are watching the video are experienced in probability, then you already know the answer to all of these, and this is very basic stuff for you, but we're still going to go over it. If I toss a 6-sided dice, if I roll a 6-sided dice, I roll it, I can either get a 1, a 2, a 3, a 4, a 5, or a 6. That's 6 possible outcomes I could get if I'm just rolling a fair 6-sided die once. And then we wanted to find the probability that I get a 6. The probability that I get a 6, how many 6s are even on the dice? There's only 1 of them, so it's 1/6. These are very easy examples, and we could get harder and harder and harder, but I said just watch the previous video. Or not the previous video, combinatorics and probability. That's one of the earlier videos on the math counts preparation playlist. So desired, possible, probability to get a 6 on a fair 6-sided die, probability to get heads on a fair coin. These are like basic examples of probability. We multiply probabilities when the events, like, let's say, like, the events are related to each other, so we'll just multiply them. But if the events are mutually exclusive, which means like 2 different events, we add probabilities. So you don't really need to know all of that because all that information is on the combinatorics and probability video. So all that information is going to be located there. I will also make future videos about going more into detail about adding and multiplying probabilities, but today's video is going to be a little bit different. So let's get into it. So we're going to solve a couple of harder probability problems, and we're going to start right here. A teacher with a math class of 20 students is going to randomly pair the students to take a test. This is one of my favorite problems in math counts. We have a math class of 20 students, and the teacher's going to randomly pair the students to take a test. What's the probability that Camila and Cameron, two students in the class, are paired with each other? So we want these two students to be paired with each other, and we have 20 students randomly paired. So, well, let's just use the regular thing. We go ahead and we see that, well, there's 20 students, we need to form a pair, so let's go ahead and that's just 20 choose 2, right? You're going to go ahead and say it's 20 choose 2, and you're going to go ahead and you're going to say it's 20 times 19 over 2 factorial, and you're going to go ahead and say that's just 190. And you're going to place 190 in the denominator, and then you're just going to put, and then you're just going to count the, we're going to go ahead and we're going to count the successful outcomes. But that's all wrong. This is all wrong. It's not 20 choose 2. It's not 20 choose 2, but then we have a problem here. 20 choose 2, because 20 choose 2 is how you can form one pair. We want to pair all the students together. So we could multiply by 10, but that wouldn't... Now, this seems really hard. We need to pair all the students. Now, there is a formula for this. There's a formula for this, how to pair M objects or M people into pairs, right? K pairs. But we're not going to do that. That's really, in this problem, that's what that looks like. It's 20 factorial divided by... So basically, yeah, it's going to be something big. It's 20 factorial divided by 2 to the 10th times 10 factorial, which is again a vague formula for the number of pairs, which is not the usage in this problem. So this 20 choose 2 thing isn't going to work here. We need a better way to do the problem. The biggest mistake that people will make in this problem is, one, they will overthink, which is what we're doing right now. We're thinking of probability as we count all the possible pairs that can be made, and then we count the successful pairs. And that's pretty hard to do. That's pretty hard to do, to count all of those things. So we're going to go ahead and relax for a minute. We're going to simplify the problem. There's a lot of ways we can make pairs. We don't want to count that. Let's go ahead and see, and just focus on one of the students. Let's go ahead and focus just on one of the students. Let's go ahead and focus on Cameron. Now this student, Cameron, if the teacher selects Cameron, Cameron can be paired with 19 students, right? Because there's 20 students, Cameron is one of them, there's 19 left. So Cameron can be paired with 19 other students. And now we already have the possible outcomes, because we only care about the pairs with Camila and Cameron. We don't care about all the pairs. That's irrelevant to our problem. We only care about the pairs with Camila and Cameron. So Cameron can be paired with 19 other people. So we can place that in the denominator as the possible. And then, how many of these are successful? We want Camila and Cameron to be paired with each other. Cameron can be paired with 19 other people, including Camila. So there's one successful outcome, and that's the one where Cameron is paired with Camila. So now we have our probability as 1 over 19. We didn't need to do any complicated combinatorics to get to the answer. We have our answer, which is 1 over 19. And that shows how you can simplify the problem by just waiting and thinking about a better way to do the problem. And this is, some people might call this common sense, but most people will try to overthink it, because if you do a lot of combinatorics, especially like when preparing for competitive math, you will often complicate combinatorics how you do the problems, but in this case, it's just not the way. So relax on the combinatorics if it gets a little too messy, and try to go to cutting the irrelevant cases out of the problem. That's 1/19. Now that we know how to do these problems, let's go on to an easier example. We use the harder example to show the common flaw of saying 20 choose 2 or 20 choose 2 times 10 because there's 10 pairs, or using that nasty formula. So let's go here. This comes from the school sprint round. 6 students, 4 juniors, 2 seniors must be split into 3 pairs. If the pairs are chosen randomly, what is the probability that the 2 seniors form one pair? Express your answer as a common fraction. So we want the probability that the 2 seniors form one pair. Let's go ahead and list out how many people there are, since there's only 6 of them. And they're different people, so S1, S2, and then there's 4 juniors. So J1, J2, J3, and J4. Alright, let's take a look at these people. They have to be split into 3 pairs. Now what we could do is we could try to break them up into pairs, count the total number of pairs that can be made. But let's look at what the problem's asking, because that looks like hard. What is the probability that the 2 seniors form one pair? Remember, we're not looking for anything. We just want the seniors to be in one pair. We want the seniors to be in one pair, and then we're done with the problem. So let's take a look at just one senior. We're going to circle senior 1. We're just going to start with senior 1. Senior 1. And senior 1, how many choices does senior 1 have? Senior 1 can be paired with senior 2, junior 1, junior 2, junior 3, or junior 4. There are 4 juniors, 1 other senior, so there are 5 people he can be paired with. There are 5 people he can be paired with. Now, we want the seniors to be paired together. Now, out of the 5 possible people that senior 1 can be paired with, there's one successful one when senior 1 is paired with senior 2. So if he's paired with senior 2, there's only one case that happens. So 1/5 is our probability, and that is our answer. We were looking for the probability that the 2 seniors form one pair. That's just 1/5. So we didn't have to do any complicated combinatorics. This is the amount of work we have to do. This is literally all we have to do. Just think about how we can just form one of these pairs without even thinking about the other juniors. We don't care about the juniors. So it's 1/5 total probability. Now, what if we pick senior 2? If we pick senior 2, then, well, it's the same thing. We have 5 choices, and one of them is successful when senior 2 is paired with senior 1. So we could have chosen senior 2 and then paired senior 2 with senior 1. That could have worked as well. And the same thing with this problem. What if we start off with Camila? Camila also has 19 choices, and one of them is successful when she's paired with Cameron. So I can have any one of these. If I call this, like, I don't know, to represent that this is Cameron, this would be like CA, and this would be like CM. Like, these both have 19 students that they can be paired with. And then 19 and one of them is successful. One of them is always going to be successful. So always remember, don't jump straight to the combinatorics. Try to slow down and cut all the irrelevant cases out of the problem.